All right, so in this section, we're going to review basic atomic and orbital theory. Now, I'm going to warn you ahead of time, this is going to look like really scary stuff. 90% of this stuff, if you don't get it and you really want to get it, come by my office hour. I think that's going to be your better bet. But if you're not understanding, a good chunk of this, it's okay. This is a lot of theory, a lot of jargon that's happening here. It's really the last 10% of this discussion that's going to be the most important. That's electron configuration. So don't sweat this too much. It's almost unfortunate that I have to talk about this so early in the semester because I think it scares a lot of people, but it's really not that important. So with that being said, let's take a look at some review material of basic atomic theory and orbital theory. All right, so let's start with electrons. So electrons are going to be really important for us in organic chemistry because it's really the electrons being shared between two atoms that forms a covalent bond. Covalent bonds are the most important type of bond that we talk about in organic chemistry, so that's why we need to know something about electrons too. So electrons, as the first little bullet point here, can be thought of as both a particle and a wave. Under some situations, the electron has to be thought of as a particle, just like any other particle, like a billiard ball or something like that. But strangely enough, we have to think of it as a wave as well, literally a wave. And we're going to see eventually that that wave that's being used to describe the electron is described by a wave function. That's a mathematical function for a wave that describes the electron. So that's where it gets a little bit tedious and hard to understand, but that's the situation here. So electrons, both a particle and a wave. Now, as a particle, of course, you can look this up. This is a common constant, but it's 9.11 times 10 to the negative 31st kilograms for the mass of an electron. So just a little fact. An electron traveling about a hydrogen nucleus has a velocity of about 2,200 kilometers per second. That's got a lot of variables associated with it, but that's a pretty fast speed as it whips around the nucleus of an atom. So just a little bullet point, again, a little factoid. The wavelength of any particle, and this includes electrons, but it includes jumbo jets as well, with mass m, so it's got to have a mass of some kind, can be calculated using what we call the de Broglie equation. We're going to take a look at that in the next slide, but anything can be described as a wave using that equation. Now, in the field of quantum mechanics, which is the modern theory that we use to describe atoms, that's the modern atomic theory, we describe electrons mathematically using wave functions. They're literally called wave functions. It's a mathematical function like y of x equals 2x or something like that, just like that. So we're going to see, though, that the symbol used for the wave function is not f of x. It's typically psi, which is a Greek uppercase symbol, psi. And then typically we have not x, y, z Cartesian coordinates, but we use spherical coordinates, as we'll see in just a second. So anyways, ultimately, these wave functions that describe electrons are coming from what we call the Schrodinger equation. You've probably heard of this before in general chemistry, and that's one of the most fundamental, probably is the most fundamental equation in the universe, and we're going to take a look at that briefly as well. So Schrodinger equation, that's the granddaddy of all equations. That's the one we're going to just take a brief look at. Now, of course, electrons orbit the nucleus, and the nucleus is where the protons and neutrons live. So most of the mass, the vast majority of the mass of an atom is located in the nucleus because that's where the protons and neutrons live. And furthermore, electrons weigh approximately 1/10,000th the mass of a proton or a neutron, and that's why all the mass effectively is concentrated in the nucleus, and the electrons orbit the nucleus. Now, those electrons, of course, live in orbitals. You've heard that term before. Orbitals themselves are not real physical objects. They're just simply put their probability density functions of finding the electron in three-dimensional space. So they're not real physical things. They're just mathematical descriptions of high probability regions where the electrons like to be. Electrons are important in chemistry. I've already mentioned that they're what make up covalent bonds, and that's why we need to spend some time talking about it and review this atomic theory. All right, so let's start with the de Broglie equation. I mentioned this already as an equation that allows one to calculate the wavelength of any particle, so not just electrons, but jumbo jets as well. And the way this equation works is lambda, which is the official symbol for a wavelength, equals Planck's constant, which is h. That's just a common constant. In fact, we use this so often in general chemistry that it's easy to memorize this pretty quickly. M is the mass, of course, and v is not the frequency this time. V stands for velocity, just like in physics. So pretty simple equation as long as we know the mass. And I should mention that the mass should be in kilograms, and Planck's constant in his joule seconds is the unit of that, and then the velocity must be in meters per second. So with that being said, I've got a quick sample calculation that we need to take a look at here. and I've got an on-screen calculator to do that. So just a quick question. This is, I already said in lecture, I think the other day, that we don't do a whole lot of mathematical equations in organic chemistry, so this almost feels weird doing this, but let's just take a quick look at a de Broglie wavelength calculation. It's pretty straightforward. All right, so what we're going to do here is we're going to look at the first part of this question. So an electron traveling at 5% of the speed of light, and we're going to try to calculate the de Broglie wavelength. So I already goofed up. The wavelength, which is lambda, equals Planck's constant, which I have memorized. You can just look this up if you don't know it. So 6.26 times 10 to the negative 34th. I have the units memorized on this. It's joules seconds. The mass of an electron I just previously stated to be 9.11 times 10 to the negative 31st. Boy, I have this strange feeling that that's in grams and not kilograms. So later, just take this with a grain of salt. I'll have to look this up later, but I think it's 10 to the minus 31st kilograms, I hope. Yeah, I think that's right, because I think 10 to the minus 27th is grams. Yeah, so I think we're okay. All right, so, or 10 to the minus 28th is grams. So mass in kilograms, and then times the velocity. So here we're talking about 5% of the speed of light. So what I'm going to do is divide by 100, which gives us 0.05 as a fraction, and then the speed of light is approximately 3.0 times 10 to the 8th meters per second. The reason why the mass has to be in kilograms is because, if you recall, the joule unit is comprised of kilogram meters squared over second squared. So in order to get this kilogram cancel, we have to, pay attention to the fact that joule has a kilogram built into it. So that's why it's got to be kilograms. All right, so let's enter this value or this expression into the calculator. So we got to hit the second button, EE, and then negative button 34 divided by make sure we hit the negative button and not the subtract button, of course. Okay, so finally, we've got a result, and paying attention to things like sig figs, I suppose. In the strictest sense, I suppose we have to say that it's 1 sig fig, but let's just call it 2 sig figs. I'm going to break the rules here. I'm sorry. And breaking the rules, this is going to be 4.8 times 10 to the negative 11th. And that's going to be meters. Okay, so that's the wavelength of an electron traveling at 5% of the speed of light. 5% of the speed of light is a pretty quick speed, or velocity, I should say, technically. How about the wavelength of a pitch baseball? I'm going to let you work on this on your own time, just to save a little bit of time. So I think you'll get the hang of this pretty quickly. You just plug in the numbers and calculate away. So, all right, so that's it. So that's calculating the de Broglie wavelength. You can do this for any particle that has a mass. And what you get on the other side is the wavelength of that particle is what you get. Okay. Now, electrons, again, in a lot of situations in quantum mechanics, they have to be thought of as waves. And so that gets this whole process started in terms of thinking about what electrons really are doing. All right, so let's go to the Schrödinger equation now. So this is the part that starts to get a little bit scary, but it's not too bad. It's arguably the most fundamental equation of the universe. It's a second-order partial differential equation, which means that, there's some pretty serious math classes that you got to take to be reasonably comfortable understanding this equation. So we're, of course, not going to do this. In fact, I took an advanced physics class as part of my chemistry major as an undergraduate, and we talked about the Schrödinger equation. But even in that class, we didn't spend any time solving or coming up with solutions to the Schrödinger equation. Because it's a partial differential equation, you really don't get a scalar answer out of this thing. What you get out of this when you apply boundary conditions, and in the case of an atom, an example of a boundary condition is, well, the electron, which is negatively charged, is attracted to the nucleus. That's a boundary condition. We apply those to the Schrödinger equation, and then we get what are known as solutions to the Schrödinger equation, and those solutions are functions, as it turns out, and the function is symbolized by psi, okay? So let me say that again. Schrodinger equation, here you see it in equation 2.2 in its spherical coordinate form. You know, when you work with this, you get function solutions out of this, and they're called wave functions, okay? Another aspect of getting solutions out of the Schrodinger equation is necessary to use so-called quantum numbers, and we're going to talk all about those in just a second. But as part of the math, you get quantum numbers to get solutions out of this, okay? So this is a Schrodinger equation in its spherical coordinate system form. It's really convenient to work with spherical coordinates because the electron is whipping around a nucleus. It's really hard to describe that with x, y, z dimensions, so typically you see spherical coordinates. Now here's just one example of a solution to the Schrodinger equation. This one happens to describe either a 2px electron or a 2py. It really doesn't matter because it's the same solution to this. And the coordinate system is r, which is the radius. Theta is that angle about the z-axis, I suppose. And then phi is the angle from the z-axis. And so hopefully you've seen this in math class, spherical coordinate system. This still looks like a scary thing, but it's actually not that bad. These are all numbers you can evaluate on the calculator. Z is the charge, so depending on the situation, Z is pretty straightforward to figure out. It's usually 1 in most cases. A naught is a constant that stands for the Bohr radius, and we'll talk about that on a graph in just a second, raised to this power. Z is the charge again. R is the radius. This is exponential raised to this power, sine theta, cosine phi. And this is the solution again for this type of an electron. So you know, the solution we get is strange. It's a wave function solution, okay? All right, so we're not done yet. Unfortunately, the wave function itself has no real human comprehensible meaning. So just because we can come up with a solution for this type of electron doesn't mean that it's really useful to us inherently. So it's only when we take this wave function solution, and strange enough, we square it. You know, we just simply take the equation, we square it, literally, and we still have this spherical coordinate system. And another aspect of doing this, which is hard to explain, so if you want to know about why r squared is here too, then ask me in office hours. That's a real lengthy explanation. But psi squared gives us the probability of any function, okay? So it doesn't even have to be an electron or a wave function. It could be a sine wave, or it could be a cosine plot. Anytime you square this like this, you get a probability function. Okay, so a new function develops out of this, psi squared, it's a probability function. Okay, now for this type of electron, 2px or 2py, you square it, you get the probability of finding that electron in this coordinate system. Okay, so that's a lot of words right there, a lot of math. I promised you, or I mentioned that, you know, don't freak out. Actually, this is not that important. It's very technical. But I still wanted to talk about it because I really enjoy this subject. And as you're going to see in just a second, I've created some new plots for this here that literally use these wave functions to describe the orbitals and whatnot. So, okay, so that's the math of it all. This is really what's important here, is that probability of finding the electron is based on squaring the wave function in the spherical coordinate system. Okay, so let's talk about quantum numbers. I mentioned quantum numbers are necessary to use when you're working with the Schrodinger equation. And for electrons, when we get these wave function solutions out of it, it's necessary to use quantum numbers, okay? Now, there's 3 spatial quantum numbers and a 4th one that has to do with spin. So let's just talk about the first 3 quantum numbers. The first one's called the principal quantum number. That's the most important one. That's the highest ranking quantum number, and it's symbolized by N. That describes the shell that a particular electron resides in. So if I say n equals 1, we're talking about a first shell electron, no question about it. If I say n equals 5, we're talking about a 5th shell electron, no question about it. The higher the shell number, or the principal quantum number is, the higher the energy and the average distance from the nucleus the electron is. So that's really important. So n, the principal quantum number, correlates to energy of the orbital, but also average distance from the nucleus. Possible values, these are the quirky rules for quantum numbers. Possible values of n are 0 to infinity. Okay, so you start at, oops, that's a typo actually. Let me fix that right now. It's not 0 to infinity, it's 1 to infinity. My apologies. So that's a correction right there. All right, so 1 to infinity, and those are integer values. All right, so the angular number, which is symbolized by L, describes the subshell that an electron resides in. So possible values of L are 0. So this time that is 0. 0 to n minus 1 integers. For example, if n equals 1 for an electron, then L is forced to be 0. And when L equals 0, that's always associated with an S subshell. So let me just kind of write some of these out here. L equals 0 is always what we call an S subshell. L equals 1 is always what we call a P subshell. L equals 2 equals a D, and so on and so forth. So that's how L works. So L is kind of, like I said, it's associated with the subshells. So depending on what the value of L is, that's the subshell we're talking about. And the last quantum number is called the magnetic number. So that's M sub L, as we say that, describes the orbital that an electron resides in. So possible values are negative L to positive L. Let's take L equals 1 and try to think about possible values for M sub L, given that L equals 1. Possible values are going to be negative 1, 0, and plus 1. Okay, so that correlates to a P subshell. And what's always true about P subshells is there's 3 P orbitals. One has a quantum number of negative 1, 0, and plus 1. And the way we kind of distinguish between these 3 P orbitals is we say P sub x, P sub y, P sub z. That's how we distinguish. So there's always 3 P orbitals. And as you can imagine, if you do the same process, let's just label this M sub L here. If you do the same process for L equals 2, which is a D subshell, you're going to find that there's 5 possible values for M sub L in this situation, which correlates to 5 possible D orbitals, and so on and so forth. And of course, if we back up a little bit, L equals 0 is an S subshell. The only possible value of M sub L is 0, and that's why there's only one type of S orbital. Okay. We're going to look at shapes of these things too, of course. Hopefully you remember this from general chemistry. S is spherical, P is a dumbbell shape, and D is a 4-leaf clover shape. Okay, so quantum numbers are really weird. But they're easy to work with. They just correlate to the shell, the subshell, and the orbital. It's not a big deal. They have quirky rules, but that's the way it goes. Okay, so let's go back to wave functions. So remember, wave functions describe electrons. They're derived from the Schrödinger equation using quantum numbers. And they're mathematical descriptions of electrons as waves, literally. Okay. So depending on what quantum numbers we're dealing with, there's a different wave function that describes that electron. Wave function has no significant meaning on its own. We square it right away, and it's only when we square it that we get a probability function. So right now we're going to take a look at a couple of these wave functions squared, so these probability functions. And what you see on screen already is on the y-axis is probability that I've plotted, and on the x-axis we have distance from the nucleus. So we're talking about a hydrogen atom, and the nucleus of the hydrogen atom is 0, and 1, 2, 3, 4, 5, 6, 7, etc., times the Bohr radius. This value right here is the constant I was talking about before. It's called the Bohr radius. And if we're talking about a 1s wave function squared that we just plotted, notice that the maximum probability of finding the electron is located 1 Bohr radius from the nucleus. That's no accident. That's true. That's how the Bohr radius is defined. Okay, so when we plot that, this is the wave function squared for a 1s, maximum probability right at the Bohr radius. Now let's plot a 2s, and notice that the probability goes up a little bit, and then it dips back down, and it just barely kisses the x-axis, and right where it kisses the x-axis is 0 probability of finding the electron. This is called a node, and let me just label that real quick so you can see the spelling on this. You've probably heard of this before, node. Okay, right where it touches it. And then it goes back up in probability, so the maximum probability is right about here. That's about 5 Bohr radii, I suppose is the plural of Bohr radius. Bohr radii, 5 of them, right about there, is true for a 2s. Now, as you can imagine, a 3s, which is a higher principal quantum number, is even further out in terms of the maximum probability. So let's take a look at that. Of course, maximum probability is here. We've got a node here, and we've got a node here, right where the 2s node is. Okay, so 2 nodes for this one. Maximum probability is about 12.5 Bohr radii. All right, so I'm going to clear these so to avoid confusion. Let's jump to a 2p. So the maximum probability for a 2p is about 4 Bohr radii, and of course if we jump to a 3p, it extends out a little bit more, so that's approximately 12 Bohr radii. Clear that real quick, and then a d, of course, is a distance about 8.5 Bohr radii. All right, so this is simply put, this is just plotting the radius, okay? We're not considering theta, we're not considering phi in terms of the spherical coordinate system, so it doesn't matter where these are in terms of theta and phi, this is just the radius, okay, and talking about probability. Now, if you caught this, I'm going to say this again, the general theme here is that the higher the quantum number is, n, the principal quantum number, the further away from the nucleus the electron likes to be. These are probability functions. Okay, so let's move on. Let's go to something even cooler than that one. So that's a one-dimensional plot, one spatial dimensional plot. This one is a two-dimensional spatial plot. So this one considers not only r, but it also considers, oh boy, I've got another typo here. Not phi here, but theta. So let me fix that. Sorry, apologies. These are brand new notes. So this should be theta, scratch. Okay, r and theta. And so it's two-dimensional, two spatial dimensions. And let's go ahead and do this again. So let's start with, unfortunately, I still haven't figured out what the bug is in my little brand new JavaScript plotter. So I have to start with 2s, because if I start with 1s, it tends to crash. So that's a plot of a 2s probability function in 2 dimensions. And the dark regions, the dark blue region, is high electron probability. And the whitish regions, of course, are very, very low probability. Now, right away, we can talk about a few things about this. This is a 2s again, so this is maximum probability is right about here. And then this white region right here is no probability of finding the electron. That's called a spherical node, because truly s orbitals are spherical, and this is just simply put a cross-section. It's a two-dimensional cross-section, and this whitish region in here is a node. That's where there's no probability of finding the electron. Okay, and then once we get past that, then this pinkish region is another area of relatively high electron density. And then, of course, out here in the white space, that's very, very low electron probability. So the darkest regions, high probability of finding the electron. Now, it's kind of random where the electron is at any given time. So, one of the things that I skipped over sort of on purpose, because we had a lot to talk about, is the Heisenberg uncertainty principle, which essentially says that it's a waste of time trying to know where the electron is at any given time, because in the next instant, we don't know where it's going to be. So think of the orbitals as just, areas where the electron likes to hang out. And so let's do this. We're going to do a simulation. We're going to start to plot or take time snapshots of the electron. And the first thing that probably catches your attention is that, in this little time snapshot, the electron's outside that dark blue region, but that's perfectly okay, because the picture that I just generated here is based on a 95% confidence interval, which means that I arbitrarily chop off these bluish regions based on 95% confidence. But of course, there is a chance that the electron is outside of this. If I had changed this value, which I can, to 100%, then you're going to see all this area as bluish region, okay? So the pattern that's developing here, as you can see, is that the electrons are mostly clustering around this high blue area, this very dense blue area, because that's the highest probability of finding the electrons. And of course, some of them are clustering near the nucleus, but less probable compared to the bluish region. All right, so I'm not going to wait for this to finish. It's going to plot probably ultimately, I think I have it set to 10,000 electrons, so I'm not going to wait around for that. So I'm going to stop this and clear this. All right, so that's a 2s. Let's take a look at a 3s. For comparison purposes. It takes a little bit longer to generate a 3s, and hopefully it won't crash. I'm always crossing my fingers here. So 3s, here it is. We've got the blue region inside here. That's a little bit of density, probability density, a little more probability density. These are nodes, these white spaces right here. And then the highest probability is this dark blue region outside here. All right, so these are once again spherical nodes, as we call them, because they're spherical nodes. I mean, they're literally in 3 dimensions spherical things. But the cross-section, it looks like a circle. And I could do the same thing about starting the time snapshots, but I'm not going to. All right, so let's move on to a 2p now in 2 dimensions. And you're used to seeing this probably from textbooks. This is the classic dumbbell shape for a p orbital. But maybe you've never seen a 3p orbital. So what happens with a 3p orbital? I think 3p is my favorite type of orbital. I tend to ask these on exams all the time. I don't know why. But it looks a lot like a 2p orbital, except now we've got a spherical node and a nodal plane, as we call it, down the middle. We had a nodal plane in the 2p, but now we've added a spherical node. And the highest probability density of finding the electron is here, but also here. And then a little bit of probability density here and here. Okay, but notice that the highest probability extends outwards a little bit. We expect that. So every time we jump up in the principal quantum number, the highest probability moves out away from the nucleus, which is located in the middle here. Here's a 3D. This is one type of a d orbital. Cross-section, of course, this is the classic 4-leaf clover shape. 4 out of the 5D subshells or orbitals have this 4-leaf pattern. The only difference between them is how they're aligned with the x and y axes. But the last one, the fifth one, is the strangest one of them all. And again, we're only seeing these things in 2 dimensions, so it gives you kind of a false sense of what's going on here. But this one actually looks like a lot like a p orbital, but except it's got a halo around it. I urge you to go online to Google whatever you have to do and check out 3-dimensional pictures of this one. I call it the donut dumbbell shape, but it's got an unusual shape compared to some of the other ones. Okay, so these are orbitals. Okay, so you've seen these before in textbooks, but you know, play around with this little JavaScript applet or whatever it's called. I created this summer. It was kind of fun. Play around with it, look at the shapes. I'm probably going to ask you some learning catalytics questions related to the shapes and spherical nodes, nodal planes. Oh, by the way, for the D subshell, what you have is you have 2 nodal planes. Here's one nodal plane that goes that way and another nodal plane that goes that way. That's classically what happens with that one. Okay, so now finally let's get back to sanity. And let's talk about electron configuration. So here's where it gets easy again. And you've seen these before in general chemistry, I'm sure. Electron configurations are blueprints for how the electrons should be arranged around the nucleus of an atom. It all relates to quantum numbers. It all relates to subshells, shells, and orbitals and this kind of stuff. So we should review really quickly the Aufbau principle and also Hund's rule of maximum multiplicity. And we should also mention a last quantum number, which is the 4th quantum number. It's called the spin quantum number, and it's symbolized by m sub s. This is not a spatial quantum number. This is spin. Okay, not in the sense that it's the Harlem Globetrotters spinning a little electron on their finger. The 2 spin states that are possible for an electron are +1/2 and -1/2. Literally, just those 2 values are possible. Okay, and nothing else. All right, so the +1/2 state for an electron is very, very slightly lower in energy compared to the -1/2 state. And that little detail is going to be incredibly important when we start talking about nuclear magnetic resonance in the 2nd semester. That entire spectroscopy technique is based on that little detail, except not for electrons, but actually protons, which is very similar in idea. All right, so the Pauli exclusion principle essentially states that no 2 electrons can have the same values for the 4 quantum numbers. So anytime you're looking at, the 6 electrons of carbon, every one of those 6 electrons has to have a unique set of quantum numbers. That has to be true. Even if the first 3 quantum numbers are the same, the spin quantum number has to be different for the 2 electrons. That's what we're saying. So let's scroll down a little bit and take a look at Hund's rule of maximum multiplicity. I have to admit that I get Pauli exclusion principle and Hund's rule of maximum multiplicity mixed up all the time, but I think I have it straight here in the notes. This is another important principle. Hund's rule says that if there are several unfilled orbitals to choose from with equal energy, the electrons that are being added to the orbital must be spaced out amongst the degenerate orbitals, blah, 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 blah. This won't make a whole lot of sense until we start doing orbital filling diagrams, and you're going to see how this kind of manifests itself in the electrons and, the electron configurations. And then finally, we have the Aufbau principle, which simply states that, well, first of all, it's a German word, which means the building up principle, but it says that the electrons fill the lowest energy orbitals first and eventually reach the highest orbitals. Now, because of this little detail, 1s orbitals are always filled first. There's no question about that. Pick any element from the periodic table and you start to do the electron configuration of 1s, always the lowest energy, always fill that first. 2 electrons can occupy 1 orbital as long as those 2 electrons have opposite spin. I think I have a misspelled word again here. Boy, I should have proofread these notes a little bit more carefully here, but sorry about that. Electron configuration, standard notation. So let's start with the basic standard notation for electron configurations. You've done hundreds of these before, maybe not 100, maybe a dozen or so. And it's pretty simple, so let's do a couple examples. Let's start with nitrogen. And the first thing you would normally do, of course, is you look up on the periodic table how many electrons nitrogen has, and I should have done this ahead of time. I'm going to go ahead and take a guess that it's 7. That's a total guess on my part. So 7 electrons. And using the periodic table is what I do these days to come up with the standard notation. I know that the first 2 electrons are going to go into a 1s subshell, and of course, if they have opposite spins, you can stuff 2 in there. The next 2 electrons are going to go into a 2s. The next series of electrons, which we should have 7 total, are going to go into the p subshell, and that's it. I'm pretty confident that is 7 electrons because I know that nitrogen has a a valence number of 5, and that makes sense in terms of that configuration. So that's the standard notation. We, by the way, the number in front here is the principal quantum number in disguise. So this is 1, meaning like n equals 1, the first shell. S is the subshell, so we assume that L equals 0 in this case. And M sub L is also 0, and that's why there's, really just an S subshell, but also S orbital is the same thing. Same goes for this. So 2 is the shell, it's the principal quantum number. S is the subshell, M sub L is also 0. We can put 2 electrons in there. Now, in standard notation, we don't make any distinction between P sub X, P sub Y, and P sub Z, even though those are 3 separate orbitals that are possible. But anyways, 2 is the shell, P is the subshell, and we're holding 3 electrons total in that subshell, and that's it. Okay, so that's standard notation. I think we'll just do one more because I think we'll get the hang of this pretty quick. Oxygen just has 1 more electron, so 1s2, 2s2, and then 2p4. All right, standard notation, standard notation. All right, so I don't think I'm going to clear the screen at this point because I think the next thing we'll take a look at is the condensed notation, so I'll just go ahead and leave this right on screen. The condensed notation is also known as the noble gas notation, so I'm sure you remember how to do this from general chemistry, but if not, take a look. So what we do in this method is we determine the preceding noble gas, which, again, I don't have the periodic table in front of me. I should have brought that online in front of myself before I started this, but I believe it's helium. And helium is the preceding noble gas, so we write it in brackets, which also means that we don't have to worry about any of the electron configuration up through helium. All we have to worry about is the electrons past helium, and that would be the 2s2 and 2p3. So condensed meaning like it's slightly easier in the case of nitrogen to write this, and same goes for oxygen. We just put a helium here. And then this one is, of course, 2s2 and then 2p4. All right, so it also makes it easy to see how many valence electrons. Just as a reminder, valence electrons, or the valence shell, I should say, is the outermost shell containing at least 1 electron, and the grand total for the second shell, which is the valence shell, is 2 plus 3. That's 5 total valence electrons. Oxygen, of course, is 6. All right, so I don't think I want to do manganese and copper. Be prepared for these electron configurations in in lecture these days. And I might have some learning catalytics questions related to this, where you're going to literally enter the electron configuration into a little box for some of these elements. Okay, so let's look at the last type of electron configuration. And I'm going to go ahead and clear this, I think, at this point. I think I have to. Okay, so these are called orbital filling diagrams, and these are really slick because it really gives us a true sense of how the electrons are filling in these orbitals around the nucleus. So what we do in this situation is we still write 1s, so still the principal quantum number, the subshell, and then here we're going to show arrows representing electrons. So if the arrow faces upwards, that's what we might call plus 1/2, that spin state. And if it's facing down, it's minus 1/2. This is one orbital that we're looking at, so the spin states have to be opposite. You cannot have 2 up spins or 2 down spins in the same orbital by definition. So up and down, and then for carbon, we've got 2 more electrons to worry about, and here's where Hund's rule of maximum multiplicity comes into play. We have to spread out these electrons before we start pairing them up. So we're saying that this is the correct configuration, or I could have moved this arrow over here, or I could have made them down. It doesn't really matter as long as I don't pair them up. Okay, so it's not this electron configuration, so this one's bad. I'm going to go ahead and mark that out. This is what's not allowed under Hund's rule. Can't do that. All right, so as we can also do a hybrid version of this as well, so we can put helium as a noble gas and then just simply worry about the electrons past helium. So that's the sort of hybrid approach is what I'm calling it. I don't think that's an official name, but that's what I call it. All right, so let's maybe do 1 or 2 examples of this. So let's do, oh no, I did manganese and arsenic. And again, I'm not looking at a periodic table. Shame on me for not doing my homework ahead of time here. So let's just do oxygen. So oxygen has 6, 7, it has 8 electrons. And the first 2 electrons are going to fill into the 1s orbital, and they have to be spin opposite. So that's done. That's completely full. We have to move on to the second shell, and the first thing that we're going to do is fill up the 2s. So this is the lowest energy orbital. This is the second lowest energy orbital. And then what we have is these 3 p orbitals. I'm going to go ahead and label these a little more appropriately. So we're going to call this one p sub x, p sub y, and p sub z. So we're literally distinguishing between the 3 p orbitals by this little subscript. And this is the little subscript xyz is associated with m sub l, that third quantum number that I was talking about. Okay, so we have 8 total electrons for oxygen. The first couple of electrons we're going to have to spread out. No question about that. That's Hund's rule in action. We can't pair them up. But the fourth electron that we're going to put in here, we can pair them up with any one of these 3. So let's just go ahead and do it here for giggles. We're just going to put it in the middle here. It doesn't matter where you put it. Okay, so that's how Hund's rule works. This is called the orbital filling diagram. Now, if you don't do the p sub x, p sub y, p sub z, I really prefer that you put a, what do you call this? Not a tilde, but a parenthesis, I guess. What are these called? Parenthesis, I guess. Not even a parenthesis. I don't know what these things are called, but I want you to write 2p like so. I want you to tie together these 3 things so I know what you're talking about, because on exams, one of my pet peeves is people, put these in here, but they don't, make any indication that these are p or whatever, so I get confused and I'm grading it. And unfortunately, when I'm confused, that's bad news for the student because I'm just going to mark it off. Okay, so tie them together, do something to indicate clearly that we're talking about p orbitals here. That's all I ask. Okay, so let's move on to something else. That's orbital filling diagrams. I think we're we're pretty close to wrapping up this section here. This is kind of a longer section, I'm sorry. Valence electrons, the outermost shell of an atom containing at least 1 electron is said to be the valence shell of an atom. We saw a couple examples of that. So the number of electrons occupying the valence shell of an atom can be quickly determined. So you don't have to do electron configurations to figure this out. All you have to do is look at the periodic table. You just look at the group number, and that's how you quickly tell. So let's do carbon. So carbon, if the question is how many valence electrons does carbon have, I'm looking at the periodic table, and I'm looking at the group, and I can tell you that carbon's group is 14 in the newest system, in the IUPAC system. And if the number is greater than 10, to figure out the valence electrons, you have to subtract 10. So greater than 10, subtract 10, which quickly means that there's 4 valence electrons for carbon. You can verify this for yourself by doing the electron configuration for carbon. You're going to find 4 valence electrons. Nitrogen is group 15. 15 minus 10, of course, is 5. And then oxygen is group 16. 16 minus 10 is 6. And we'll just kind of round this out here. Fluorine is group 17. And the number of valence electrons is 7. And then here, what's below helium? Neon is group 18. And that's, of course, 8 valence electrons. So we're kind of building up to the octet rule, of course. We know that, I'm sure you remember all this stuff from general chemistry. The noble gases are very happy elements. They're very stable because they always have 8 electrons in their subshell, and that means that they're happy elements. It's when we're deficient in valence electrons like fluorine or oxygen or nitrogen, these elements don't like to have unpaired electrons. So what they're going to want to do, especially in the case of these 4, so carbon, nitrogen, oxygen, fluorine, they're going to want to pick up, in carbon's case, it wants to pick up 4 electrons. Nitrogen wants to pick up 3, oxygen 2, and fluorine 1. That's why we typically see carbon make 4 bonds, nitrogen 3 bonds, oxygen 2, and fluorine, all the halogens make 1 bond, and then the noble gases don't make any bonds. So there's a connection, okay, as we're going to see. This is a really important detail, especially as we start to put together in the next section Lewis dot structures. It really makes it quick and easy to figure out what the bonding situation is based on this little detail about a valence electron. So really, it's an important detail. It seems simple enough, but it's incredibly important when it comes to structures. All right, so this was a review of basic atomic theory. I know there was a lot of wicked stuff in there. Don't sweat this too much. Don't panic too much. It's really not that big a deal. I think if you figure out electron configurations again, review it, or maybe you knew it all along, we're going to be golden. Okay, so be prepared on, coming up this week to answer questions related to electron configurations and perhaps a couple of questions related to quantum numbers and also some of the theory that we talked about. All right, so that's it.